strike the materials. Whew, I'm ready.
All right.
All right. I'm confused.
You're just excited because Blake's not here.
Yeah, he smells bad.
You know, he is going to watch this video.
That's okay.
Just saying.
Blake, you smell bad.
There's so many new people.
Years from now, there's gonna be someone completely unrelated whose name is also Blake. and just
Exactly.
hurt their morale.
I'm just going to leave it. You can hurt somebody. Don't talk. They're prospective students.
I'm just looking.
I mean,
Hey guys,
just they knocked it up.
I was about to. Oh, that's odd.
Now it's even more, now it's even worse.
So many classes where like tourists go by and they just kind of stare in.
You just kind of sit up.
It's almost like being at the zoo though, when you go to school and they like come walking through.
We
Or
should
like
have
animals.
get like little.
Yeah, don't be,
Hey, it's not there yet.
you're here a minute early.
Man, I'm glad you're not sick.
Huh?
Glad you're not sick.
I got mine right,
As long as you have a prescription.
There he is. She's getting
I suspect we're going to end up doing a couple extra bonus problems today because I get to thinking these problems aren't going to take that long to solve. So,
so. Are you free after this class? So?
I am available for you, kid. As long as you bring that cookie that you dropped by earlier.
I did. I have it, it's right here.
And Joy pointed out, yeah, she brought you a cookie, but I said she didn't need it. Well, no, you weren't here to help, so.
It's the exchange rate these days.
Yeah.
Huh.
Look
Yeah, I
at
gotta
you.
play Blake
Oh.
today.
Jesse's moving over.
I am.
Oh.
Hey, let's just banish Blake.
He's moving over in
This is
life.
the end of the road.
All the way down there.
Yeah, I'll fill in for Blake today whenever we need a free body diagram.
Okay.
Is Blake, is the video on right now?
Yes, it is.
Hey Blake, guess what Jesse and I are doing tomorrow? Going to gun range without you.
I'm
Sorry about it.
I was almost thinking that you were gonna wait for the response there.
Yeah, that's right.
Blake,
Sorry about it.
hey Blake, know what we're doing tomorrow?
Yeah, okay.
No? Okay, okay.
All right, it's 3 o'clock, let's get started. We're just gonna do problems today. Let's jump into number 6-20 up there. Are we ready?
Yeah. You see, Carson karate caught my pencil, so I wasn't prepared.
6:20, draw the shear and moment diagrams for the overhanging beam. It's not really an overhanging beam. It's not really good. It would only be an overhanging beam if the beam extended beyond point B.
It's hanging over the other beam of the wall.
Nice. Got him.
Funny guy, funny
The
guy.
sass though.
Okay,
Oh,
so,
Ben is definitely the sass master.
so where shall we start?
Free body diagram.
Free body diagram.
Sorry Blake.
Thank you, Blake.
All right, free body diagram.
What?
Is he an Iowa?
He's on his way to Iowa.
Yeah, he's.
Let's see, it's 10:30, he might be in Iowa, no, probably not.
Are
Probably
they
not.
heading towards Iowa?
They're heading toward Iowa, they left at 10:30 this morning, so,
So,
probably not there yet.
Still?
All right, here's my beam, what's my free body diagram, what do I do?
Put our distributed force on
All
there.
right, put the distributed force on,
Sorry, dude.
down, yeah.
Sorry. Got plenty of food again.
And the peak is 3 kips per foot. All right, what else?
Reaction forces at A and B.
Reaction force A and B? What kind of reaction forces do I have?
Well, there's gonna be a normal force at A pointing upward,
Mhm.
and also, I guess there probably doesn't have to be one, but there could be another force at A in the parallel direction of the beam.
But there's no other.
Yeah, but there's no external forces in that direction.
I'm just clarifying that there could be one, right?
Okay.
Just from my own understanding.
Yes, all right, why don't I just draw A and B then? There's A and there's B, okay. Any other forces? Apparently not. All right, so there's our free body diagram, what's next? Solve for A and B, okay? How would I solve for A and B?
Take a moment about.
resultant, or is it, what do we call the resultant?
Sum of moments.
It's the result
Yeah, find the resultant of the triangular.
of the distributed force. So you're saying find the resultant of the triangular force.
Mm-hmm.
Okay, what is the resultant of the triangular force?
3 times 12, what is that? 2/5, from 8?
3 times 12, is that what you're saying?
Divided by two.
Divided by 2.
And 1/2 3 times 12,
Oh, is that basic math?
right? And that would equal then 18 kips. And where am I going to put it?
2/3 from the left side. Of
What
the
distance from the left side?
2/3.
8 feet.
8 feet. All right, so it's going to go in here, right about there. Okay, there's my breakdown of dimensions.
And then I'll do the sum of the moments thing, the common one.
How about what?
Okay.
Okay,
Could we go about either point,
sure.
even though B can't technically have a moment on,
Right, but it cannot support a moment,
okay, yeah.
right? But there can be moments that sum to 0 about point B, just like there are A, because neither A nor B can support a moment.
Right, okay.
Some of the moments about A. What are they?
18 times 8,
8 times 18.
and that would be, coupling is positive, right? So that's a positive moment.
So, again, this is where we came back to before. So the moments, when we're talking about sort of the moment diagram, is about the cupping or the not cupping, right? The cupping or the, whatever the opposite of cupping would be, right? That's for doing the shear moment diagrams. But in the context of, because if you think about it, right, we had beams last time where we had this kind of a thing going on, right? And we said those are both negative moments because they were, but when I'm summing the moments, this one is positive and this one is negative. Those two are equal and opposite moments in order to compensate. You know, the whole beam has to have those to be equal and opposite. You see what I'm saying? So in terms of the moment vector, we still use the vector notation of positive and negative. And so this one, my R is here, my force is down, it's into the board. That is a negative moment. But when we go to do the moment diagrams, we track the relative moment along the length as positive or negative based on cupping, tension on top or tension on the bottom.
And why can't we just do that with regular sign convention,
Do what?
our diagrams?
We'll get to it in a minute when we show that, when I show you the diagram. Okay. This is again, this is the same thing Caleb was wrestling with last time. In one case you're treating it one way, in another case you're treating it another, but you have to be self-consistent. That's the consistency we choose. Okay, but that's one moment. What else do I have? What's that?
18 times B
Plus 18
times B vector.
times f sub b. Right? So we know then f sub b is equal to 8 kips. Now what?
Sum of forces.
Okay, sum of forces, FA plus FB minus 18 equals 0, and we find FA equals 10. Okay, so now we have all the forces. So I can come back up here, make this one 10 kip, to make this one 8 Kelvin. Now what? What's that?
Oh, I got the sheet there.
Shear diagram. Okay, let's do a shear diagram. Where am I going to start?
Do we just pick spots, so could we go A and go to the right? Start at A and go to the right?
Well, we start at A and go to the right, yeah, I mean, but generally positive is to the right, so you're going to start, I mean, you can do it either way, but I recommend starting at A and moving to the right, because it's,
Okay, so let's start at positive 10 kips,
I start at a positive 10.
and then we go down to -8.
Where?
Well, maybe not.
Where will we be at -8?
At 12 feet, we would have a,
So when we come out here to 12, and you want to be at -8.
we would have a straight line connecting from 0, 10 to 12, -8.
That's what you're saying.
Yes.
How does everybody else feel about that? Jesse agrees? What about the three of you? Ben? Are you shaking your head or are you just thinking? You're disagreeing? You're doing it so subtly though. I object! I got Caleb's attention. Okay, so I got 2 in favor, 1 opposed. Kayla, we don't have an even number, so we should be able to get a,
Well, wouldn't it be parabolic instead of straight line because you do the integral of?
okay. So, Clayton, where are you gonna fall on this? With Ben?
I just don't know.
Okay.
I don't know.
So Kayla's saying it should be parabolic. Because, if you recall, we talked last time about the fact that V, or actually delta V, is the integral of W of X dx. Right? Remember that expression from last time?
Mhm.
What is W of X?
Isn't it three
So,
X?
W of X is equal to 3/12 X. It's equal to 3 when we get to 12 feet. You see what I'm saying? The slope of that line is 3/12,
Yes.
right? So the integral of, x over 4, which is exactly what that is, dx, becomes x squared over 8. Oh, not dx. From 0 to 12, right? So the functional behavior is going to be parabolic. So now it's going to be a straight line. And the question is, does it curve this way or does it curve this way? Oh, here, wait. Does it curve A or B?
A.
Who votes for A? A? Okay, that's the majority. Because the biggest change happens at the end. Right? The biggest increment of force occurs out here at the end. Okay. Then what does it do?
Then it's just gonna go to a straight line to 18, and then go back to 0.
Straight line to 18,
Runs. Yeah,
like that.
right.
Is that what you're advocating for? Okay, and I should actually go back and, since this was delta V, if I actually wanted to do the real V, it would be the integral of, it's gonna be equal to 10 minus x squared over 8, because it starts out at 10. X was 10, and it drops off from there. And this is all a negative force. So this is actually, I should have said minus. Being a little cavalier and getting to the point where this parabolic, I should have been more careful. Right, because the force is negative, not the function, the force. All right, so that's the shear diagram. Anything we want to do with the shear diagram before we move on? There's one more thing we're probably going to want to do with the shear diagram.
We'll look at maximum shear.
Close. Yeah, it's sort of the right idea, but not quite there. All right, we'll come back to it. Let's go to the moment diagram.
Is it from 0 to 10 at 0?
Yeah, but I don't bother.
So it's not the point you're,
That's not the point I'm trying to get to now.
We want to find the point that has zero stress on it.
Right, we're going to find the point of zero shear. Why is this point important? What happens when the shear is 0? What happens at the point where V equals 0?
Maximum moment.
Right, the moment is a maximum at the point where shear is 0. So that'll help us make sure we get our moment diagram correct if we know that the maximum moment occurs at the point where V equals 0. So what is the point where V equals 0?
Eight feet.
Hmm?
Is it 8 feet?
It is not at 8 feet. It is just shy of 9. 0 equals 10 minus x squared over 8. So x squared equals 80. X equals, let's see if they've got it in here. 8.944. So the location where we cross here is 8.944. Okay. Essentially, that's the point where, excuse me, the area under this curve compensates for the applied reaction today. All right, now what else? What do we do for the moment diagram? I'll put my 12 and 18 in there. What do I do next? So I know where to start.
We start at 0, don't we?
Why do we start at 0?
Why?
Why?
Because whatever end we start from, there's going to be 0, there's going to be a 0 moment.
Right. Both ends, neither end can support a moment. They're both,
Right.
they're both, neither of them is a rigid connection. So we're going to start at a 0 moment on both ends. And so we know we have those two data points. And we know the maximum occurs at 8.944. So it's up here someplace. So now we just have to figure out some kind of a graph, some kind of functional behavior between those 2 points. What should it look like?
the integral of
So M is going to equal whatever the moment at A is plus the integral of V Right, so we have whatever we started with, plus the integral along the way. Moment of day is 0, because it can't support any, so it's just the integral of 10 minus x squared over 8. Which is?
And x minus x cubed over 24.
What's that?
Plus,
Plus c.
well, from 0 to 12.
All right, from 0 to 12. Well, yeah, but m, this is actually m of x, right? Maybe we're actually trying to generate a functional behavior. We're not actually trying to evaluate what the total moment is from 0 to 12. Right? So it's a cubic polynomial. But we know the point up there is it's going to have some kind of a thing that looks like that. Okay.
What about the rectangular area on the shear diagram at the nth grade? How does that factor into?
Hold on a second. Let's get back to, somebody's supposed to yell at me for what I've drawn.
Okay, you didn't take into account the last part of our shear diagram.
All right, so Kayla in particular, I was waiting for you to say, no, I said from 0 to 12,
Yeah,
not from 0 to 18.
which is why I was just staring at the board confused.
Okay.
I lost both.
So 0 to 12, it does that.
Lost this
So where does that end?
way. Straight line from there to.
Well, no, where does it end? What's the value at which it ends? What's this value?
48.
What's that?
48.
How do you get to 48?
Table.
Plug in 12 for x.
Yeah, you plug in 12, right? 48. Trace your words, I didn't check that, hold on. Yeah, 48. Make sure. Did you plotting the function? Yeah. Okay. So then, what did you say? We go from there?
Straight line,
Straight line,
there all the way to 18.
and there all the way to 18. And you can actually work at it backwards if you wanted to, because the space in this graph is 6 by 8, which is 48, right? So we know that the space in the end goes from 0 to 48. So you could actually work at it backwards as well. Yes?
When we found our maximum point, could that have also been a negative maximum?
It could
or
be, it could be a minimum, right? So if you have a bend in the other direction.
Right, okay.
But in this case, it's a cup, so it's a positive value. Okay? And I suppose if you have a complex enough function at the top, you could have multiple zeros. Right? You could have a minimum and a maximum both, or local minimum and maximum. That's this thing.
If you have branding,
What's that?
if you have branding curves on top and bottom, or like.
So, right, if you have, that's what I'm saying, if you have a very complex loading system, right? Because you've got to be able to support both upward and downward forces distributed along the beam to be able to get multiple crossings. Okay.
Multiple crosses, that's my family.
What's that?
Multiple crosses is my family.
Exactly. Woo. All right. Does everybody have any questions about that? Does that make sense?
Yep.
Okay. All right, let's do the second one. Shear and moment diagrams for a cantilever beam.
Yes. Yes, that's first.
What do we do first?
We can go free body diagram.
For 100, Alex. All right. Is that a two-piece thing, or is that just a,
Moment.
it's a single beam, just a moment apart? Okay. applied here at a point that's 1.5 meters in. And then we have a force applied out here, that's 2 kilonewtons. Another 1.5 meters. The moment in the center is 3 kilonewton meters, and it's cantilever beam. Okay. Anything else I need to draw on my free body diagram?
2 kilonewtons upward A.
2 kilonewtons upward at A,
And a reaction moment today.
and a reaction moment at A. Do I know the amount of the reaction moment?
3 kilonewtons. Oh, no, it's not.
No, it's not 3 kilonewtons.
Plus 6.
Right, so the moment at A, so the sum of the forces was easy, because there was only 2 of them. So they didn't have to do sum of the forces to find the reaction force. But the sum of the moments is equal to minus 3 kilonewton meters. What else?
2 kilonewton meters minus 6 kilonewton meters.
Minus, right, so 3 meters times 2 kilonewtons, so 6 kilonewton meters. Anything else? Anything else? Huh? Plus the moment of A, right. So MA is equal to 9 kilonewton meters. Okay, my free body diagram done now? Okay. So, what do my graphs look like?
The shear graph is
So up
pretty easy, just up to and then all the way up and then down.
All right, so the shear graph is pretty straightforward. Up, over, and down. Because I just have the 2 applied forces. What about my moment diagram?
Start negative 9 kilonewton meters.
Start at negative 9 kilonewton meters. Why do you say negative 9?
It's the value of the start, it's negative.
Right, so you have a 9 kilonewton meters here. The moment is positive from a vector sense in terms of summing the moments. But from the diagram standpoint, it is causing the bottom to be in compression, and therefore we start at a negative value. Okay? So that, all right. So now where do I go from minus 9?
Straight line up to point 1.53,
Positive 3 or negative 3? I'm not sure I understand.
positive 3.
So you're saying straight line up to that point?
Yeah.
Caleb's not sure.
Isn't it still negative 3 because it's also causing?
See if we can get a consensus from the room. Would it be positive 3 or negative 3? Another vote for positive.
I think it's positive, because it's at some point in the middle between those two, it's gonna have to be zero, right?
Why?
If they're opposing each other.
But they're still causing the
Yeah,
launch one on.
Right, so this one is still causing it to be in compression on the bottom.
Okay, so
It's
it's
on
from
the
the
top.
top three.
They're opposing each other from the vector standpoint, but from the moment shear diagram, or the moment diagram, they're both causing it to be cupped downward. Okay. So you're saying now, I should connect it to that point. Is that what you're saying?
Yes.
Wait, but according, then the moment at the very end of the beam is also gonna be bending it down, putting the bottom under compression.
I'm not sure what you mean by the very, on the right end of the beam?
Right, the moment.
So
that's
if I'm out
caused by-
here, it's still gonna be negative, is what you're saying.
Right. So
Yeah, it can still be negative, I mean, I've still got room between -3 and 0, I can still be negative.
Click on -6.
You throw in -6. All right,
Oh, yeah. Because it would move by 3.
okay, we have three choices now, +3, -3, -6. Anybody want to throw something else in, or somebody want to rally behind one of those?
42.
I'm gonna say it's 9 straight over to 1.5 and then
Straight horizontal over?
horizontal and up to -6.
Great.
And then a line from -6 to,
Okay, how do we find the moment diagram? How do we express the moment?
Integral.
The integral, right, and we're actually not doing it, right, so this is delta m is the integral of v dx, right, so that m is equal to whatever I have at a plus the integral of v dx. The moment at some point x is equal to the moment I start with, right? What's v dx, or what's the integral of v dx from 0 to 1.5? Boys? What's the integral of v dx from 0 to 1.5?
through
3. So that says that my moment is going to change by +3. So the utility of having this is I know where I start, because it's whatever's applied, and then I move by +3 to bend to -6 in going between those 2 points. Right? Then what happens? What happens at 1.5?
There's a negative, a moment of -3 kilonewton meters,
There's a moment of -3 kilonewton meters.
which should just be a straight, a vertical line
Yes, a vertical line to where?
back to 9, back to -9. It's still negative.
Just going to 0.
Well, that's supposed to be 0. That's actually what happens. Right, up to here, I just have the -9 plus the integration of my v. Okay? 3 of that -9 are this applied component. So once I move to the other side of that, once I move past that, I've lost -3. If I subtract -3, then I'm moving positively. And then I continue to integrate that out.
Well, why are you subtracting -3?
Because I
You'd be
have,
adding.
what's that?
I feel like you'd be adding -3.
So, what we're measuring is the internal moment. This is the moment within the beam, right? So I got a lot of moment over here, I have less moment out here, right? And you can think of it, again, you can think of it as coming in from the right-hand side. I start at 0, and I begin to build moment by integrating the curve, right? And since I'm going from right to left, it's becoming more negative, right? So this area here, from going right to left, is a negative, an increasing negative value. Down to the point where I'm just to the right of that, that end of the beam only has -3. 2 times 1.5. Right? But it's negative, it's still bending it in the downward cupped position. I jump across here, now I've added another -3 to it. Right? Now it's cupped, there's more, it's more strongly cupped. Does that conceptually make sense?
No, I mean, that's the way I thought it should look, I was just sign conventions.
Yeah, that's the hardest part probably of doing this, because it's not like the traditional vector sign notation. You know what I'm saying? So it makes it more challenging because of that. But if I applied, and I applied this negative, if this was 0, I'd start at 0. If I apply a negative, then it's -9, right? So I move up and down based on what is or isn't there. If I take away that -9, I move upward. Right? If MA disappears, my graph moves upward. If I take away the -9. As I move across here, I'm taking away the -3, so I move upward. Does that help at all? Because what's internal to the beam here is no longer, it's only impacted by what's still out here to bend it. Right? I no longer have this piece bending, so this piece is acting to bend here. It's not having any effect on this. If this force were in here, I'd have no moment out here at the end.
Right.
You see what I'm saying? Because once, if I bend a piece of, if I take where's my ruler? Meter stick's gone. All right, I guess I have to do something very small. If I bend this guy in here, I got a lot of bending moment in here, I get nothing out this end. Right? So as I transition from here to here, this negative all in here, but out here I've got nothing. So as I go from negative to that side, I increase because I'm removing the negative moment. So as I move from here to here, I'm removing this negative moment that's bending the section. Yeah. Thanks. Okay, do you want me to do the mirror stick or you
No,
good?
no, I mean, I understand it, it was just sign convention was kind of being difficult.
Okay.
But, I mean, that's exactly how I thought it would look.
Okay. All right, are we all good with this picture? This moment diagram, is that all I'm supposed to do there? Yeah. So we've got 15 minutes, we can do another one. Let's pick another.
Let's do it.
334. Now, the danger here is, I have no idea what I assigned you guys for homework.
That's okay.
Let's do something that's a little more fun. 632 looks fun. Those of you watching the video, this will be in the homework next time. Or in the example problems next time. Is it in the homework? Does anybody know?
What is it?
632? You have no idea. All right.
I haven't got to look that far.
Homework? There's homework? What? Smooth pin is supported by two leads A and B and subjected to a compressive load of 0.4 kilonewtons per meter caused by bar C. Determine the intensity of the distributed load W0 of the leads on the pin and draw the shear and moment diagram for the pin. Okay, so they've given us a free body diagram of the pin. Distance here is 20 millimeters. These are all in millimeters. This is 60 in the center and 20 on that end. And then we have a loading condition here on the top. That is 0.4 kilonewtons per meter. And then we have, oh, I should have moved these down a little further so I can draw them. Loading conditions in the bottom. It's 20 millimeters 60 millimeters and 20 millimeters. Okay. So first we're supposed to find out what W naught is. And then draw the shear moment diagrams. So how do I find W naught? Roy do? How am I going to find W naught? I'm going to start calling on people individually.
You find the resultant voltage,
Okay, and set it equal to,
and then sum the forces.
right, so what are the sum forces going to sum to? 0, right. So I'm going to sum the forces, set it equals 0. Because then what we're doing to find a resultant force. Right, the resultant force is 0, so that's what I'm saying, there's not really a resultant force.
Like of each
Oh, of each section,
piece.
oh, of each piece, okay. Okay, so what is the resultant force in the top piece?
Point oh two four newtons.
0.024 newtons? No,
Kilonewtons.
0.024 kilonewtons.
Didn't see the K, sorry.
Yeah.
Kilonewtons.
So it's just the area of the graph, or the area under the W of x curve. So the area is the base, which is 0.06 meters, times the height, 0.4 kilonewtons per meter, bad K. So that gives me 24 newtons. Right? Plus, is that positive or negative? Just for kicks. Positive or negative? It's negative. Sign convention says downward is negative. So what's the other piece? What's the upward force? I mean, it's going to be 24 newtons, but how would I express it in terms of W naught? How do I calculate the force? How did I just do it here? What did I just say?
The ideal point of the times.
Okay, how do I calculate the force? I don't want just the answer, I want to make sure we know how we do it. The force here was the area in the curve, under the curve. So the area under these curves is what I'm looking for, right? What's the area under a triangle? Right, 1/2 base times height. The two triangles are symmetric and equal, so it's just base times height. The base is 0.02, the height is W naught. So W naught is equal to 24 divided by 0.02, which is 2,400, 1,200. Is that right? 1.2 kilonewtons per meter. Okay, so it asks for W naught. W naught is 1.2 kilonewtons per meter. Now, let's do the shear and moment diagram. Is everybody okay with that? Very good. Okay, now let's do the shear and moment diagrams. Where's my shear going to start out on the left? Say it out loud, please.
0.
0. There's no force on the left-hand side. The far left end is experiencing no force. What's going to happen to my shear diagram as I move to the right?
write down.
It's cute. Negative gravel.
Negative gravel,
It's gonna go,
so like this,
yes.
yeah. So that the shear is negative at this point.
Outside dimension.
Oh. No, it's gonna go the other way.
It's gonna go positive, because things that rotated clockwise are positive. Remember from there's a picture in that I drew last time, I think I drew it last time, here. No, that's not a good picture. Yeah. I drew the little thing I had, right, I had V going here and V going here, right, and if it's clockwise, the convention is if you're rotating clockwise, if the shear causes the beam to rotate clockwise, it's positive.
So, does that make the left W not stuff positive and the right W stuff?
So,
No.
so what is the internal shear within the beam? Right, so in other words, well, think of it last time. We started out with a force that was like this on a beam, right? That's what we had, that 9, whatever, right? It was pushing upward on the beam, right? That's what the last, yeah, pushing upward on the beam. It's 2 kilonewtons, not 9, right? Pushing upward 2 kilonewtons, right? The shear, I'm sorry, the V, right, is positive all the way across, because this is constantly causing it to rotate in a clockwise direction. Right, if I took a little section out of here, that little, if I sectioned the sample right there, there's an internal shear that's downward to compensate for that. Both of those cause it to rotate in a clockwise direction. So anything that's here, that's applied out here, that's going to be upward, then there's going to be an internal shear in the downward direction to compensate, and the net effect is going to be to rotate the sample clockwise. So it's going to be like this. Right? Are we good? Okay. And that goes out to 20 millimeters. What's the value of V at that point?
W net.
Um,
It's gonna be area and W.
Yeah, W not times.
It's gonna be, net times 20 millimeters divided by 2.
Right, so
Whatever that is.
0.01 times that, or 12. We see that? Okay. Effectively, what we're doing is, remember V is going to be V at A plus the integral from 0 to x of omega of x dx. Right, that's the full expression for V. This is the delta V part, and VA is whatever we start out from the left. Right. So this is a positive area, because the forces are positive. So I must be integrating a positive area, I have to be increasing my function. And I increase it by that positive area, which is 12. Okay? Now what happens at 20? So here I'm going to go back and put my 60 and 80 out there. No, that would be 80 and 100. Okay, so what happens now going forward from 20?
We're gonna do negative shear.
I have negative shear.
What's the, do we have the resultant up there of
It's gonna
0.4 kilonewton meters times 60 millimeters?
Yeah, I think you can do that in your head.
What's the 24?
Right, negative 24.
So we go down from 12 negative 24
No.
at 80, and it's going to be a straight slope line.
So I'm going to, you're saying I'm going down here to
Negative 12.
to negative 12.
12 minus
So
24.
you're changing by 24.
Yes, sorry. This
Okay. And it's going to be a straight line, you say?
Mm-hmm.
Everybody agree with that straight line?
It's gonna,
Then we have an opposite curve after that.
Oh, you're doing the next thing already.
yeah.
Okay. So I was looking for a yes. Yes, I agree with the straight line. Because again, we're integrating a constant.
Mhm.
So if we integrate a constant, we get a linear. So we integrate a constant, we get a line, and it's negative because it's pointing downward. And then, Kayla, would you like to demonstrate again, please? Okay, you're doing, I'm a little teapot, short and stout.
That's exactly what it
Here
is.
is
It's a
the
little-
handle, here's, okay. All right, and then it goes
we got that
up
on video.
like that.
Yeah, we do.
Oh, I have the power of editing. Okay.
I mean, if I
So-
said you hired somebody to do
Yeah, and I have the power to, you know,
It's going to just go
tell
down.
them, okay, cut that little section out in the center. Anyway, okay, now that we're back, so, does it end at 0?
Yes.
Yeah, because the end, you know, we have no net forces, we don't know what the applied moments, okay? Good. So, what's my moment diagram gonna look like?
the integral of that.
Okay, so again, just like we had before, moment equals the moment applied at A plus the integral from 0 to x of v dx. So we're going to integrate this. What happens when you integrate this? You get something cubed, right? So is it going to be positive, negative? How's it going to, what's going to happen? Positive and concave up. Hold on a second, let me draw my 20, 80, 100. So you're saying, again, like that? Okay. But if this is of the form kx squared, this will be of the form k over 3 x cubed, right? What's the value at the peak?
K times 20 cubed.
Okay, so what's k? So let's go back. Let's go back to the beginning. We're running out of time. Oh, I'm out of time. Do you have to go?
Yeah.
Yeah, all right. So what you would do is you go back and you say, okay, well, omega, or w of x is equal to whatever this thing is, right? Right, so it's the slope of this thing, right? It's a linear slope, and that's w naught over 0.02 times x. Right? The rise is w naught, the run is 0.02, which is, actually that is the slope. That is the slope. Right, that's what,
So it's just going
so it's just omega over, yeah, so it's just be omega x, which means w naught, not omega, which means that the k here, w naught over 2 x squared, that's that functional behavior, right? so that when x is 0.002, 0.02, we square that, we get 0.0004 divided by 2.0002 times omega naught, which is 1200, and we should get 24, or we should get 1200. Is that right? We don't know. Anyway, that's how you would get through. Okay, the slope, find your omega naught, and then find the values up here. Anybody want to guess what the other part, what the next part looks like? Just quickly. Just characterize it, just qualitatively.
It's gonna be parabola.
Gonna be parabola, up or down?
Down. Concave down.
And then change halfway across.
Is that concave up?
It's gonna be concave up. Because I'm still increasing the area. Right, the area under my V curve is still continues to increase, so this goes up. It reaches a peak at the midpoint.
Wait, that's concave down.
Oh, sorry, it's concave down, you're right, it's concave down, but it.
That's not what I was thinking anyway, so.
Yeah, you were thinking
I was
like this.
thinking,
Yeah. So it would come up like that,
hmm,
because we're still increasing the area under the M curve until we get to here, and then we start decreasing the area under the V curve. And then symmetrically comes back down. And the key is then just to go back and quantify this slope so that you can then solve for V directly and then solve for M directly. You go to your office. As soon as I get a check off, yeah.